Good morning, everyone. Welcome. I might give it actually a minute or so for folks to log on. But welcome to our fourth and final installment of our Affordable Housing Electrification Training Series. We're happy to round out our session chatting about understanding electrification, technology, operation, and maintenance today. So again, I'll give it a few more seconds as folks trickle in before I go ahead and dive in. Okay, looks like we have a pretty good number here, so I'll go ahead and kick it off. Before I go ahead and dive in and dive into the agenda and introduce our speakers, I just wanted to pause to take a moment to thank our sponsors and program partners that really helped to make the entire electrification training series possible. Without Wells Fargo, Energy Efficiency for All, and programs like LIWIP, SOMAH, Build and Camera, again, we wouldn't have had this series for the second year in a row. So thank you to all of our partners. And just a few housekeeping rules and logistics here. Our recording and the presentation will be recorded today and shared out via the partnership's YouTube channel. All of the recordings from the sessions will be housed there, so stay tuned for those recordings if you want to come back on the material or share with colleagues. Additionally, we will be sharing out the slide deck from the presentation early next week. I believe we'll also be sending out last week's session as well. So make sure you're signed up to receive those emails. And lastly, we will be reserving some time at the end of the presentation for Q&A. So if you have questions, go ahead and type those up using the Q&A box in Zoom, and we'll make sure to carve out some time to answer those questions again at the end of the presentation. Without further ado, I want to introduce today's speakers. I'm Rachael Diaz. I'm a program manager here at the California Housing Partnership on our sustainability team. I'll be sort of your moderator here. But more importantly, I'm joined by two experts in the field. We have Jack Aitchison, who is a manager in energy engineering at the Association for Energy Affordability. He provides a lot of great work and technical assistance on a variety of clean energy programs throughout the state. So we're happy to have him here. And we're also joined by Mark Puchalski from the Tenderloin Neighborhood Development Corporation, or TNDC. He's a director of facilities, and we're really excited to have some firsthand experience of how to actually integrate some of these practices and, real properties. So excited to hear from him as well later on. And in terms of our agenda for today, after we get through these housekeeping slides, I'll pass it over to Jack to walk through operations of all electric buildings. And then we'll hear from Mark on best practices for modern multifamily housing. And lastly, hopefully there's time. I want to spend a few minutes introducing one of the partnership's programs, the Solar and Multifamily Affordable Housing Program, that has some really substantial rebates to help cover the cost of solar on properties. And of course, lastly, we'll be carving out Q&A as mentioned to address any questions that folks have. So again, use that Q&A box as those ideas and questions come up. We're happy to help answer. Without further ado, I'll go ahead and pass it over to Jack to kick off our presentation.
All right, thanks, Rachael. Appreciate it. My name is Jack Aitchison. I'm an energy engineer with the Association for Energy Affordability. I've been working on multifamily electrification projects over the last 5 years. And fortunately, in my role, I get to be the one that gets called when things go wrong in these electrification retrofits. So I have a lot of experience sort of troubleshooting and seeing where the points of failure of all electric buildings happen. So I'm going to share some of our best sort of practices for operations and really operations and maintenance of all electric buildings. Next slide, please. So here's the agenda. I'm going to start off with some heat pump basics. Really, heat pumps are a catalyst to the electrification movement in California and really all throughout the US. So we're going to talk about really the fundamentals of a heat pump so you can better understand how to maintain and how to operate that equipment. Then I'll go into some myth busting of gas mixed fuel buildings, operation and maintenance versus all electric buildings, operations and maintenance. Then I go into some detail, excuse me, on some very specific system types. So HVAC, water heating, cooking, and solar PV. Now, I gave this webinar last year and went into a lot more detail on the individual systems. So I know there's a link to the recording of last year's presentation. So if you're interested in more detail on those sort of maintenance sections, you can review that. I won't go over those slides today, but you will get those slides when you receive a copy of the presentation as a PDF. So just wanted to flag that if you want to learn more about that all-electric HVAC and all-electric water heating maintenance and those other sections as well. And then I'll dive into the importance of utility monitoring building management systems, which is really going to lead in to what Mark is going to talk about how the plan to integrate building management systems in the TNDC portfolio and how we can use it for all electric buildings. So really excited to have Mark join me this year. Thanks. Next slide. So heat pump function and components. Next slide. So starting off with what is a heat pump? Effectively, a heat pump is something that moves heat from one space to another. A refrigerator is how a refrigerator works is it is pulling heat out of the refrigerator. So in that enclosed space, it is pushing that heat out of the refrigerator. If you ever put your hand behind the back of a refrigerator, you're going to feel heat. That's effectively how a heat pump works. Heat pumps work. It's going to draw heat out of the surrounding air in heating mode, and it's going to push it into the space. Now, the nice thing about heat pumps is that it can reverse that refrigeration cycle, so it can heat and cool a space. So all air conditioners are heat pumps, but not all heat pumps are vice versa. All heat pumps are air conditioners, but not all air conditioners are heat pumps because air conditioners can't reverse that cycle. So it's the same technology that we've seen for several years now. It's just utilized in a different way. So really your refrigerator, a drinking fountain, an air conditioner, if it can reverse that cycle, it is that refrigeration cycle, it is going to be considered a heat pump. And then you have your heat pump water heater on the right. Next slide, please. So in layman terms, a heat pump is a device that moves heat from one place to another using a refrigerant, just like an air conditioner or refrigerator. Next slide, please. So what is so great about heat pumps and why are they so important for the electrification movement? Well, they're hyper efficient, and that's really the key here. Heat pumps, because they're moving heat, not generating heat, they are super efficient, 3 to 5 times more efficient than gas or electric resistance. And if you take the cost of 1 BTU of gas versus the cost of 1 BTU of electricity, gas is going to be cheaper. But if you start to consider the efficiency, right? If heat pumps are 500% efficient, they're going to be drawing less energy to create the same amount of heat. And so that's where you sort of counteract that difference in costs. Now, gas prices are likely going to go up as we move to more all-electric buildings. However, for now, heat pumps are really important because they have that extra efficiency that make electrification more feasible for a lot of people. Enable zero emissions buildings. If you don't mind going back one slide, sorry, thank you. Enable zero emissions building via carbon-free electricity. If you're getting if your electricity source is from carbon-free sources, then you can have a zero emissions building. Improves indoor air quality and outdoor air quality. You're not gonna have any combustion in your building. Improves safety, no gas lines. Really the key here and what we'll be focusing on in this presentation is deliver heating and cooling with a single system. On your HVAC side, if you have cooling in your building and you have a mixed fuel building, you're going to have 2 separate systems. With a heat pump, you can do heating and cooling with one system, which is going to reduce your maintenance needs. And then also heat pumps can work in different climates. A lot of folks say that because heat pumps draw heat from the surrounding air, they you can have places where cold climates may not be applicable or heat pumps might not be a good application in cold climates. Heat pump technology now can operate as low as -30 degrees. So unless your area is often falling below -30 degrees, you can find a heat pump that's going to meet your application. Next slide, please. So I'm not going to go into super detail here. just real basic, just to understand how a heat pump works and the use of a refrigeration cycle. So this is a basic diagram of a refrigeration cycle. Start on the left with the evaporator. So what the evaporator does is it's going to change that refrigerant from a liquid/vapor mixture into a vapor. And when it goes through that phase change, when it evaporates, it's going to pull in heat from the surrounding air. Then it's going to go through a compression cycle. So see that dotted line, low pressure versus high pressure. Pressure in a refrigerant and really, all substances is synonymous with temperature, right? As the pressure increases, the temperature is going to increase as well. So by going from low pressure through a compression cycle to high pressure, that vapor goes from subcooled vapor to a superheated vapor just through applying pressure to it and pressurizing that vapor. Now we're on the hot side. As it goes through a condenser where it's phase changing from a vapor to a liquid, it's rejecting heat. So it's pushing that heat out. So that's effectively how a heat pump works. The evaporator pulls in heat and the condenser pushes heat out. Now, in a heat pump, it can reverse that cycle. So you'll see in the following slides that I'll be calling it a coil because the condenser can be the evaporator can be the condenser in a heat pump. Really, it's just a heat exchanger coil, and it can reject heat on either side because it can reverse the flow of the refrigerant. Next slide, please. So myth busting, next slide. All electric buildings are more expensive to operate and maintain than gas systems, but is this really true? So I'm gonna sort of debunk this myth. Next slide, please. So the way I'm gonna debunk this myth is talking about deferred maintenance and what happens in electric appliances when you defer their maintenance versus gas appliances. And then I'm gonna talk through the different maintenance needs for gas appliances and electric appliances and compare them. So starting off with electric appliances, really focusing on heat pumps, right? When you defer your maintenance on any equipment, you're going to lose efficiency. And when you start with such a high efficiency, let's say 400 to 500% efficient, if you're the sort of those high efficient heat pumps, if you see a reduction in your efficiency, that's going to significantly increase your consumption of electricity because you could go from 500 to 200 due to deferred maintenance, 500% efficient to 200% efficient due to deferred maintenance, and you're going to see a visible increase in utility costs. So I think this oftentimes perpetuates that myth that electricity or electric appliances cost more to operate. If you maintain them properly, they should stay high efficient and you shouldn't see that impact on your utility bills. In addition, you're not going to see the dangerous issues that you typically see with gas systems. Next slide, please. For gas systems, it's very different. Because they start at such a low efficiency, even though if you have deferred maintenance, you're going to see a reduction in efficiency, it's not going to result in a visible increase in utilities. So if you're operating a building, you're often not going to see a significant increase in your gas usage if you have deferred maintenance on your gas system. Take a furnace, for example. If we're at an 80% efficient furnace and it goes to 65% efficient, that's a marginal increase of consumption to still meet the same consumption of gas to meet the same load. So it's not going to result in a visible increase in utility costs. Now, what we do see with gas systems is they become dangerous. Oftentimes, we can see dangerous issues at the appliance itself, gas leaks, high carbon monoxide, backdrafting combustion gases into the unit. These are things that you have to actually test to find. And we find them quite frequently when we're working on a project that we do combustion safety testing. I have some data here on the left, just a summary of some of the projects that I've worked on. Surveyed 1,200 dwelling units, and we saw about 50% of them had some sort of combustion safety issue, whether that was dangerous or preventative. Preventative is like a recalled gas line connector that are prone to leak, that sort of thing. But ultimately, what you can take from this is that our deferred maintenance on our electrical appliances, we're probably going to see an increase in utility costs. And so from the building owner, you're going to notice that. But unless on the gas side, unless you actually test for it, you're not going to see these dangerous issues. So you may have the perception that you don't have to maintain the equipment as much because it's not increasing your utility costs. But in reality, you could be potentially having dangerous issues at the appliance itself. Next slide, please. So now I'm going to jump into HVAC maintenance. So types of electric HVAC systems, we're only going to be focusing on heat pumps. This is what it actually looks like, what a heat pump looks like on the left. Next slide. They come in various sizes and configurations. I showed the refrigeration cycle at the beginning of my presentation. This is a more detailed refrigeration cycle. I'm not going to go into super detail again here, but I just want to show sort of the different components and what they actually physically look like. On the left are your heat pumps. Those are your outdoor units. That is going to contain your compressor, your outdoor coil, your expansion device, really everything on the left of that diagram in the middle. And then on the right are your indoor components. That's going to be your indoor coil. And then on the bottom, you have your packaged heat pumps. These are heat pumps where it's located inside the unit. It's on an exterior wall, and all of the heat pump components are located in that one package unit. Next slide. So items that you need to maintain in heat pump HVAC. Starting off with air filters, you're going to have an air filter on the indoor coil. That is filtering the air that is returning back to the coil to be reconditioned and sent back out to the dwelling unit. That can be through ductwork. That can be through a single head unit if you have a mini split system. But you have an air filter that needs to be cleaned. If you don't clean it, you could run the risk of reducing the airflow over the indoor coil, which is going to reduce the efficiency. You can also start to get gunk on the actual coils themselves. So another maintenance item that you need to do is inspecting and cleaning your heat exchangers and coils. And then if you have ductwork, you need to clean your ductwork as well. Like I mentioned, in last year's webinar, I went in a lot more detail. I went over air filters, duct cleaning, heat exchangers, and coils, how to clean them, how to inspect them, in a lot more detail on how often to do, or what best practices are for how often to do those maintenance items. That is going to be included in the recording from last year's webinar, and also the slides that you get will have more detail there. But given the time, and I want to make sure I have enough time for Mark to cover his section, just going to keep it very high level. Next slide, please. So this is a pretty important slide here. This is HVAC electric versus gas maintenance. So starting off, electric heat pump and heating and cooling. Really, this is just illustrating the fact that when you have a heat pump that provides heating and cooling, and you have existing cooling in your building, you compare that to a mixed fuel building where you have a furnace and a split air conditioner. All of the things that you need to do to maintain your split air conditioner are the exact same things that you're going to need to do to maintain your heat pump. Just if you have a gas furnace, you're going to have to do additional things, which are the check for gas leaks, measure carbon monoxide and combustion gases, check ventilation drafting, burner inspection / cleaning. Now, these maintenance items are really preventative for dangerous combustion gas issues. However, based on the data that I shared and the testing that we've seen, people often don't do these maintenance items, and they should be doing these maintenance items. And so you can imagine that the perception is that gas appliances require less maintenance, but in reality, you should be doing this. And you're probably, if you're not testing for these items, one of these items could be true in your existing building. So just calling that out. Next slide. All right, now moving on to domestic hot water maintenance, types of electric DHW systems. Again, we're just going to be talking about heat pumps. Next slide. This is a sort of in between the two diagrams that I've shared, but this is again just a refrigeration cycle on the left. We have our evaporator. Remember that what's absorbing the heat, that's your air to refrigerant heat exchanger, that's absorbing the heat. That refrigeration is going from a liquid vapor mixture to a vapor, excuse me, and it is absorbing heat as it goes through that phase change. It goes through compression, becomes a high pressure superheated vapor, and then it goes through the condenser on the right. Now, the only difference between a heat pump water heater and a heat pump HVAC is the refrigerant to water, well, the main difference, I should say, refrigerant to water heat exchanger. Instead of rejecting that heat into the space to heat the area, that refrigerant to water heat exchanger is rejecting the heat into the water, and that is how it heats water. Now, another sort of small difference is that Lots of heat pump water heaters don't also cool the water, but there are some that do in some cases. Next slide, please. So what does this actually look like in the field? You have your heat pumps on your left. These are going to be your commercial heat pumps. These are going to have all of your heat pump components in it, your compressor, your refrigerant to water heat exchanger, your air to refrigerant heat exchanger. Then you're going to have piping to a storage tank. And this is going to be water piping, not refrigerant piping. So you can see on the left, you have your heat pumps. On the right, you have what your storage tanks look like. And then on the bottom there in the middle, those are your residential heat pump water heaters. Those are combi units, so that all, or package units where all the heat pump components and the storage tanks is just one unit. Next slide, please. So items to maintain on a heat pump water heater. You have your air filters, you have your air to refrigerant coil slash heat exchanger, you have your refrigerant to water coil heat exchanger. These are effectively very similar to a heat pump HVAC, and the way that you maintain these are very similar. Cleaning the air filters, inspecting the heat exchanger coils, cleaning the heat exchanger coils. Now, one thing I will note, in the slides that go into more detail on how to actually maintain this equipment, there is a yellow tag that says difficult, that sort of flags the difficulty to help make a decision on whether you would like to maintain this through a contractor or do it with site staff, depending on the nature of your building and who's there at your building, who works there. I will say heat pump water heaters are more complicated in terms of just the technology. And so, typically these are harder to maintain than a HVAC heat pump. Other things to be considered: DHW distribution maintenance. So crossover is the unintended mixing of hot and cold water in your hot water distribution. This is not specific to heat pump water heaters. This can happen in all buildings. However, and usually happens at like shower cartridges or mixing valves where they have failed and cold water is leaking the hot water line. However, they disproportionately impact the efficiency of heat pump water heaters more than gas. Heat pump water heaters start at such high efficiency. As they start to degrade in efficiency, you're going to see that in your utility bills. So it's really important, if you have a heat pump water heater, to be considerate of crossover and replacing those shower cartridges and avoiding crossover issues that are going to increase your utility costs. And then hard water maintenance as well. This is really dependent on the location of your property, but in terms of the pecking order of water heating equipment that is impacted by hard water, you have your tankless water heaters, which are the most impacted. Then you have your heat pumps. Then you have your sort of standard gas water heaters and boilers that are less impacted. The reason for that is heat pump water heaters have really small flow paths through that refrigerant to water heat exchanger, so they're easily clogged through scaling from hard water. Next slide, please. So DHW electric versus gas maintenance. Excuse me. On a heat pump water heater, you have an air filter. Gas water heaters, if you have a condensing gas water heater, you'll have an air filter. Crossover prevention, really you should be doing this for both. However, it's going to affect your heat pump water heater's efficiency more. Sacrificial anode rod, really this is a piece of equipment that is in every storage tank. So regardless if it's gas water heating or heat pump water heating, you're going to have to inspect that. Flushing heat exchangers for hard water. Like I said, tankless gas water heaters are disproportionately affected by hard water. Then it would be heat pump water heaters. You don't really need to do too much hard water consideration when you have a boiler or a tank type water heater, or I guess not as much. And then you have all of your sort of gas specific things like checking for gas leaks, measuring carbon monoxide, checking ventilation and drafting, and burner inspection and cleaning. Next slide, please. Moving on to induction cooking maintenance. Next slide. So we, in a lot of our projects, are pushing for induction cooking rather than electric resistance cooking when we're retrofitting gas cooking to an electric counterpart. The reason for this is that really what it comes down to is tenant satisfaction. Induction cooking offers an excellent cooking experience. And earlier I said that heat pumps are like the catalyst to electrification. Well, induction is a close second. People typically don't really care about how their water is being heated or the appliance that's heating their water, as long as they have hot water. People really care about their cooking. So Induction is a great option. It's cleaner, safer, there's no combustion, so it provides healthier kitchens. It's really high end, so there are marketing opportunities. Utility cost savings, they're probably minor, but they are more efficient than electric resistance and gas. The operations side of things, excuse me, replacement costs are higher, so reserve replacement budgets need to be adjusted. Induction cooking, the cleaning, the surface is very similar to an electric resistance glass smooth top. However, induction, even though it can boil water a lot faster than electric resistance, the actual surface doesn't get as hot, so you don't get like that burnt crud on the glass top that's hard to remove as much. So that's a benefit. Insurance credit, because of induction technology, it is a lot less prone to fire, and there's a significant reduced risk of fire. So hopefully in the future there might be some insurance credit there. And then induction only works with certain pot and pan sets. Most pot and pan sets work with induction, but not all. And so if you're undergoing this retrofit, consider providing a cook set for the folks that live there, especially if you're operating in an affordable housing building. Next slide, please. So next we'll be talking about solar PV maintenance. So when you're thinking about operating an all-electric building, one of the things that you really should be thinking about is solar, right? If you're able to offset your electricity load and all of your end uses are electric appliances, you're going to see significant utility savings. So the best electrification projects are one that pair with solar, and those are the ones where you're going to see significant reduction in your operational costs. Electrification is more cost effective with PV, common only or tenant offset. So when you're doing an electrification project and you're adding PV, you need to be considerate about, do I want to offset just my common area, or do I want to do tenant offset as well? That's going to result in net energy metering or virtual net energy metering. SOMAH requires virtual net energy metering, and I know we have some slides on SOMAH later. Coordinate PV electrical work with electrification electrical work. If you're upgrading your electrical, make sure it's PV friendly, so that when you do your PV scope, you don't have to tear out things that you just installed. We typically recommend electrification first, PV second, so that you can get a better understanding of your new electrical loads in your building. It's predictable, but it's better just to have like a baseline of actual usage. Engage with the utility early on for pre-connection approval. Pre-connection can take some time. This sort of leads into the next section and my final section, which is performance monitor. Oh, sorry, can you go back? Performance monitoring system and setup. And really you want to have performance monitoring and set up alerts based on kilowatt hour production. Don't set up alerts based on cost. Rates change. What shouldn't change much is your PV production. And how to maintain your PV system is through monitoring, visual spot checks, and then clean panels to improve efficiency. So if you have if you start to see a degradation in your efficiency, you know it's probably time to clean your panels. Excuse me. Sometimes panels can break. I've seen panels be hit by golf balls. Probably didn't know that your panel wasn't working or your solar panel wasn't working. If you have performance monitoring, you would be able to see that. Next slide, please. All right, utility monitoring. So the importance of utility monitoring, if you take anything from this, my section of this presentation is that when you electrify a building or you're operating an all-electric building, what's really going to be your indicators of if you're not maintaining your equipment properly is going to be your energy usage and result in your utility costs. So use utility monitoring software. That's a really cheap option to sort of manage and review and see if your utilities are increasing. Similarly, make sure you're tracking actually energy use, not cost, because cost can change. However, the drawback of using utility monitoring is it's going to be at least 30 days since the issue started occurring before you see the issue and know to react. So that's where building management systems have a leg up, where they can give you real-time data. So there's lots of options for building management systems, and I know this is what Mark is going to talk about. Ensure BMS works with existing equipment, and then you get real-time data and alerts. what to look for: unusual spikes of energy usage. These can indicate that the system is not performing properly and in need of maintenance. Make sure you consider solar PV and changes in uses based on season. And then, like I mentioned, set up alerts based on energy usage. And as you have, if you integrate a BMS system in an all-electric building, if you go through the slides that are that will be shared out, you'll see typical frequency of changing air filters and typical frequency of when to maintain your different equipment. As you have a building management system, you can be more predictive and get a better idea of, for your specific building in your specific area, how often you need to address those maintenance items. So building management systems also help you be more efficient from that standpoint as well. And I'll pass it along to Mark.
Well, thank you so much, Jack, and thank you, California Housing Partnership, for having me here today, and welcome, everybody. I get the privilege of talking about electrification technology, operations, and maintenance. Now, I want to preface this, that we're focusing on the multifamily housing aspect of this, but what I'm going to discuss today can really cross over to a lot of different industries. These are good practices that I've used in shopping centers and high-rise buildings and industrial applications and multifamily housing. So I hope you enjoy this presentation. I'm going to enjoy giving it. Let's go to the next slide. All right, so we're going to talk about control systems a little bit. We're going to talk about data-driven management. We're going to talk about predictive maintenance strategies, and we're going to talk about life cycle analysis. And you'll see how all this ties in together within the presentation. Next slide. Okay, control systems. Now, this is one of my favorite topics. So I want you to stop and think about the buildings. Now, when I have a history as a chief engineer for 20 years, and then went into operations and maintenance and management. When I would train a new apprentice within the engineering group, I'd always tell them to look at the building as you would look at your own body. And remember that we build for humans. And so the buildings that we occupy operate very much like our bodies operate. If you think about it, a building breathes, it draws in supply air, it exhausts bad air. It has a central nervous system, which is your electrical system. It has pulmonary, it has a heart, it has pumps that pump fluid throughout your building. It consumes, it has waste. So when you kind of look at the building in that regard, it helps kind of break down the components of this huge complex that we're in. It makes it a little bit easier to understand. The control systems, as you probably have guessed by now, is the brain of the building. So without a control system, your building is pretty much on life support, and each system is operating independently of other systems. And that's not the most efficient way to operate your body, nor is it an efficient way to operate a building. So modern control systems act as that central nervous system of electrified buildings, or any building really, but particularly for electrified buildings. There are a lot of benefits to having a control system. Think of it this way: if I walk outside or any of us walk outside and it's really cold outside, your body's control system recognizes the temperature change. It starts to constrict your pores, starts to bring blood closer to the heart and to the mind to protect the body. It reacts to its conditions. When we put a control system in the building now has the capability, a broader capability, to react to the conditions that it's in. Simple example of a very simple control system is a thermostat, right? Now, way back in the day, we used to show up to a building and we'd have to literally turn on each piece of equipment, fire up the fans, fire up the equipment, monitor it, log it all day long, make adjustments. And then we discovered pneumatic controls, and we used air pressure to control certain aspects of the building. And then we went to electro-pneumatic, where we started transitioning out of pneumatic into electrical controls. And from electrical controls, we birthed the modern direct digital control systems that we have today, where computers are doing the thinking for us. And we'll talk about some future technologies later on in the presentation. The operational benefits are obvious. It's the speed of response, and it also provides situational awareness to you, the operator of that building, so you understand what's happening in that building. Just like you want to know what's happening in your body, this feedback loop helps you really kind of look at what's happening in the building and what kind of decisions you need to make sure that that building is operating at peak efficiency. So I can't understate the importance of a control system in the building, and control systems are rapidly expanding their technology and their capabilities. And with AI coming up, it's going to be amazing what's going to happen. Now, this doesn't come cheap. There are cost implications to this. And so while the initial investment can be daunting, it can be kind of high and intimidating, it's often, when you look at that and the return on that investment, it's worth it. It really is. Even over in the short term and the long term, having that capability, there are hard costs that you'll see a cost savings, but there are also soft costs in terms of equipment, uptime availability, technician capabilities. You can automate some tasks that used to be done by hand. So there's a lot of benefits to the control system. So don't be too intimidated by that big price tag. There are ways to create an ROI to sell this. And you also don't have to build it all at once. You don't have to get an entire control system for your building. In some of our buildings, because we're nonprofit affordable housing, we don't necessarily have the budget to outfit an entire building. So we start small. We start with a component or a piece of equipment, and we can build off of that and start adding equipment and start interfacing those pieces of equipment through the control system. Just like your body does, your body talks to different aspects of one organ is reliant on another to work. The building is the same way. And what a control system does is it helps you look at that, plan it, and then really have that situational awareness that will get you in a highly efficient building, especially with the new technology with electrification. Next slide. So the importance of data in managing O&M equipment can't be understated. It is about data. Like I gave you the example of you walking out into the cold or walking out into the heat, or just how your body constantly pulls in data, your eyes, your ears, it's all data. This is just a computer, just as much as the control system is that computer. And it's bringing in all this tremendous amount of data. What's good for us is that our brains are capable of managing this data automatically. I'm not sitting here thinking, don't forget to breathe, or don't forget for my heart to pump. It's all automatic. So a control system in a building operates the same way. It makes things happen that need to happen just like we do in our body. It automates the building. But that data collection is extremely valuable information. It's valuable for the building to operate properly, but it's also valuable for you to make business decisions and understand when a piece of equipment might be coming to the end of its useful life, or when a maintenance item needs to take place. And we'll talk a little bit more about preventative and predictive maintenance strategies later on. But all of this drives into decision making. It drives continuous improvement. If I'm taking care of my body and I go and I work out, right? Or I go to the doctor and I get an EKG and I take my blood work and it looks at my cholesterol, that is data that I use for continuous improvement. The building can give you that same information. And I'll give you a simplified version of that. So if I have a current transformer measuring amperage on a fan motor, and that amperage starts going up, and the fan motor is rated at 10 amps, but I'm hitting 9.5 the first time, and 4 months later I do it again and I'm hitting 10 amps, and then 4 months later I'm hitting 10.5 amps. That's information that tells me there's a problem with that motor, right? And now extrapolate that across the entire building and the functions of the building. Just like your body, it gives you pain. It says, I got a problem over here. I think it's is it my kidney? Is it this? And as we get older, we get a lot more of those. But the building then gives you that feedback. So you're not surprised. It reduces downtime. The last thing we want to have is our boilers to go down and we don't have hot water. And we're going, why didn't anybody know? The control system will tell you. It'll start signaling. It'll start saying, hey, look, my temperature is fluctuating. I'm not able to maintain temperature. This is a problem. I'm seeing high pressures on my system that I shouldn't be seeing. All this data comes back to the operator and they can start making decisions. You can also create alerts and alarms within that operating system to let you know, so you don't have to go through and pile through tons of data. You can set it up so you get the more important data every morning when you come to your office. You can have it go to your cell phone. You can have it text you and say, hey, I think I've got a problem. So Just like your body says, hey, I stubbed my toe and it really hurts, right? If we didn't have that data management to say, I better stop hitting that thing with my foot, you would keep hitting the thing with your foot until you had a bigger problem. Well, that's what happens in buildings. If we're not aware that there's a problem because nothing's telling us there's a problem, then the problem grows bigger. It doesn't heal on its own. We're as operating engineers or as maintenance folks or as facilities professionals, we're the T cells in the body running around making sure everything's up to snuff, right? We're the healers of the body that is the building we operate. Next slide. Okay, so let's talk about maintaining the building because this is important as well. This is the crux of what we do, and that's my segue with the T cells. So when we're looking at preventive maintenance is really, I get a quarterly task list. I'm going to change the filters. I'm going to check the belts. I'm going to check my pressures, do an amp reading, right? And then next quarter, I'm going to come in and change the filters, check my belts, do an amp reading, do these things. And I'm going to do that. And I'm going to change those filters because that's what it tells me to do. Whether I know those filters need changing or not, my work order says to change those filters. So that's what I'm going to do. However, sometimes those filters need to be changed less frequently. Sometimes they need to be changed more frequently. So how do we measure that? Well, a control system can tell us how to measure that, right? And that's where we started getting into predictive maintenance. So predictive maintenance, with that same filter change, I'll put what's called either a magnehelic or I'll measure a pressure drop across that filter. As the filter starts gaining dust and debris, it's harder for that air to get through that filter. So there's a bigger pressure drop from the fan pulling the air through the filter on one side of the filter to the pressure on the front side where it's being pulled in from the outside. That pressure drop can be measured. And then that can send me a signal to say it's time to change your filters. So in some cases, like I said, if you're changing that filter on a quarterly basis, you might be wasting money. In other cases, you might be putting your building or your tenants at risk by not changing the filter often enough. Let's say you have a construction site next door that's kicking up a lot of dust. That would cause your filters to be changed more often. Or let's say you're in a very clean environment, the filters are on the roof and they don't get that dirty. You're spending money you don't need to spend. So that's how control systems can help you really fine-tune your maintenance strategies from a preventive maintenance strategy, which if you don't have any maintenance strategy, definitely get a preventive maintenance strategy in place first. And then as you build out your control systems, as you build the brain for your building, and you start telling the brain what to be on the lookout for, things like filter changes, amp draws on motors, all that can be measured. And that's information that then you can use to make better decisions. So the body is telling you what it needs instead of you just going, well, I'm going to keep doing this until I'm told not to do this. So you want to assess your current practice. You want to look at what are we doing today? The existing preventive maintenance schedules identify areas where a data-driven approach might help and start the process of building out that control system and that data input and output so that you can start migrating to more of a predictive technology, much like our bodies. The Internet of Things sensors, there's so many different ways to put sensors in buildings nowadays, from water intrusion to, of course, we have temperature sensors, pressure, vibration. All these can be feedback devices that can tell you the health of your building. If your motor has a bad bearing and starts shaking, a vibration sensor can kick that back to you and say, this is a problem, right? I'm about to blow up and I need you to come over here because this bearing's about to fry out and I could lose my fan motor and do damage to the equipment. So if you're monitoring that and you're setting parameters against your operations and maintenance manuals and your specifications, then you can follow that and make the decision at the appropriate time. So if I'm going to hit, again, with that 10 amp fan motor, I want to be triggered when it hits. As I put it in new, I'm running at 7.5 amps. When it hits 8.5 amps, maybe I want to know about that because there's a problem. Doesn't mean the motor's going bad. It could mean that there's a bad bearing. There could be some restriction. There could be an adjustable shiv that went out of alignment that's causing us to draw more amperage. But it tells the technician, go check that out before it becomes a catastrophic issue. Before you get that call Friday at 4 p.m. just before you're heading out for the weekend that, oh my gosh, we don't have air, we don't have hot water in the building. This is your way of you managing the work instead of the work managing you. And I think we can all appreciate how much that would benefit our lives. I know for me, I don't like to be managed by the work. I like to manage the work and be in control of it. So as you develop your predictive models, you're using learning algorithms to analyze historical and real-time data to make real-time decisions. The beauty of this is that with the control systems, a lot of those decisions are going to be made for the real-time aspect of it. The control system is going to say, I have this much humidity, I've got to make this change to the system to combat that, to keep within this range. The temperature is this, the vibration is, and it can start making modifications to itself, but it also can give you that, hey, I have a problem and I need your help. Now, all this sounds great, but it's not going to be great unless you train your maintenance teams. So technology is screaming fast, right? Every 3 months, we have a whole brand new technology coming out. Focus on training for your teams. Technical training for your team is worth its weight in gold. In fact, your team should be looking at technical manuals and keeping themselves up to date on the latest trends and understanding how buildings work. And technical training and refreshing that technical training is very important. So as Jack in his presentation talked about how heat pumps work and how all this works, that was very high surface level. There's a lot of different components, from oil separators to the thermal expansion valves to everything else that you need to know within those systems. Your technicians need to understand it. And even if they're not the ones doing the repair, maybe you vend out a lot of that work, you still want to understand what the contractors are working on. You want to understand how that system works just as much as you should want to know how your own heart works, right? The more you know, the better prepared you are to deal with issues and prevent those issues from coming to fruition, right? That gives you that predictive capability, that ability to see into the future. So look at it that way. Predictive technologies, predictive maintenance is really you seeing into the future. So then you can go to your capital improvements budgeting, you can go to your OpEx budgeting and say, I know I'm going to have to replace these components within about 6 months. And that can help you do that. Next slide, please. Okay, so now that we know how to maintain our equipment, and we talked about preventative to predictive maintenance strategies to get us out of reactive strategies, now we have to talk about the life cycle of the equipment, right? So let's start with the circuit. So we got acquisition and installation. I'm going to find the right piece of equipment that works for our application. What do I need? What kind of heart do I need? What kind of lungs do I need? What kind of equipment do I need to make the body building work as efficiently as possible? So now you've made that decision. And part of life cycle, there's two aspects of life cycle that you'll see. If you Google life cycle analysis or you Google life cycle, you'll see two different versions of it. One is a technical version, the life of the equipment itself. I put in this piece of equipment, it ran for 20 years, and then it died. It finally died. It's not repairable. It doesn't make financial sense to keep repairing this equipment. We need to upgrade, and so we get a new piece of equipment, and the cycle starts all over again. The other aspect of life cycle analysis is regards to environmental decisions. I want to know, from mining the ore to this piece of equipment that as I'm now ready to install, did I make the most environmental choice? How much impact to the environment did this piece of equipment have in production? So those are two different life cycle. I'm going to focus more on the technical aspect of life cycle management, but that's another aspect to keep in mind in terms of life cycle management is, what does it mean in terms of the environment? Because the electrification is about climate change. It's about the environment. It's why we're all doing this. So you get the equipment, you get the acquisition, you do the installation, you do the operation and maintenance, which we just talked about, and then you're looking at upgrades and modernization, because technology, as I stated, is moving rapidly. So as we get to that upgrades and modernization, then you're managing that equipment, and then you get to the end of the life of that equipment. And then when it reaches its end of useful life, you have to look at proper decommissioning for environmentally responsible disposal. And at this stage, you're also now planning for the replacement which then completes the cycle and brings you back to acquisition and installation. Next slide, please. All right, so what's the importance of life cycle management? Why are we doing this? Well, financial optimization. Life cycle analysis gives you a clear picture of where you're going to spend your capital dollars, when you need to spend those capital dollars. You want to understand the full life of that equipment, and there's a lot of different data points to understanding the life of a piece of equipment. How many hours a day does it run? Is it 12 hours? Is it 24 hours? Is it on demand? What are the operational conditions? Is the piece of equipment next to a body of salt water, which is very corrosive? So when you look at all that data, how many preventive maintenance have I completed against how many corrective maintenance or reactive maintenance came up, right? So when you measure all these different algorithms, and I built my own life cycle analysis program to bring all this data into play, it really helped guide me to understand when that equipment was too expensive to maintain and when we needed to actually replace that equipment. And it provides, as I said, environmental responsibility we talked about, but then operational excellence. So you're really looking at uptime for your equipment. You don't want to have downtime for your equipment. You don't want your tenants to call you and say, I don't have any hot water because you forgot to plan or you didn't plan the life cycle and your equipment just died. Then it's the most expensive to replace it. Everything takes a big toll at that point. Next slide, please. All right, so a lot of challenges, but there are also a lot of solutions. So data management hurdles. So the influx of data can be overwhelming. So invest in a scalable cloud-based data analytics platform, and a lot of control systems come with that platform built in. And then train your staff on data literacy. They need to understand what that data means and how it impacts their decision-making. And also, I'll go back to implement data governance. You want to make sure that you're controlling this data because bad data makes bad decisions. So you want to ensure that your data integrity is intact. New control systems with legacy infrastructure is going to be challenging. We talked about coming from turning things on to pneumatics, to electro-pneumatics, to DDC controls. There are phases that you can bring in through this process. It doesn't have to be all at once. So look at integration strategies and talk to your vendors and your control systems vendors to talk about how we can integrate slowly in order to keep the building continuously improving. And then look at financial considerations. So explore financing options. There's performance contracts, green bonds. There's, in some cases, you can get rebates and incentives. So don't be afraid of the cost, attack the costs and find ways. There are ways to pay for it. There's ROIs you can write up, and it is a good business decision to go down that path. All this will be available to you in the slide deck, so I'm not going to read everything, but understand the concept of it. And next slide, please. All right, so what's the future going to bring us? This is kind of exciting, especially with AI coming on board. It's both exciting and terrifying. So pretty soon we're going to have, I'm sorry, Dave, I can't do that for you. And that's what I'm expecting when someday I'm going to be in my office, God willing, and I'll say, turn up the temperature, Bob or Dave, and he's going to say no, because it's not energy efficient. But so AI-driven operations is coming. AI is here. AI is only going to get stronger. AI is going to be in more applications. The Internet of Things will expand to create much more densely connected ecosystems from microgrid technology, where your building will start talking to the grid, will start talking to other buildings within your portfolio, and the grid will talk. So there's a lot more integration that's going to be happening outside of just your building, and a good control system can help you integrate with that Internet of Things much better. And so embrace that. Next slide. And so in conclusion, embrace technology. Technology improves life. It can be scary, it can be expensive, it can be daunting, it can be confusing, but you can learn it. And technology is getting better, it's getting more user-friendly, so embrace technology. Shift to predictive strategies. See in the future. Predictive strategies equals I can see in the future. Preventative says, I see what's happening now, I do it whether it needs it or not. Predictive is where we need to go. And through AI and new technologies and even current control systems, you can get to a predictive maintenance platform. Think about life cycle. Think about the birth of that equipment to the death of that equipment and the rebirth of new equipment and the upgrades of equipment and when that makes sense. Life cycle analysis and life cycle thinking is very important for your budgeting and for operating the building. You will have, with a good life cycle program, you will have less worries because, again, pair that with predictive strategies, and you're literally seeing in the future where you can absolutely plan both financially and technically what you need for your building. And then, electrification is rapidly evolving, as I said. So stay informed, be interested, check it out. It's really fascinating stuff that's coming out down the pike right now. So there's a lot of great technology that's already out there, and there's a lot of new technology that's on the horizon. So continue to adapt, continue to look at this and realize that don't be static, always be moving. Change is inevitable. Be the foster of that change instead of the victim of that change. And next slide. Thank you for your time. I appreciate it. My contact information on that slide, and I can't thank everybody enough for letting me talk about these topics I'm very passionate about. And I'll turn it back over to Rachael.
Thanks so much, Mark, and thank you, Jack, as well. I think we've had a really jam-packed session with a lot of helpful information. I think for the remainder of the few minutes we have left, I will skip through the SOMAH slides. I really recommend that folks pop back in here and take a look, but at a high level, SOMAH is available. There's over $500 million available to new affordable housing multifamily projects that want to install solar. On average, SOMAH covers 50 to 75% of project costs, if not more, and it can be stacked with the ITC. There's also a lot of free TA baked into the program, and long-term maintenance and monitoring support is also baked into the program. So it fits nicely into the theme here. But again, if folks are interested and want to learn more, I recommend either reaching out to me directly, we can set up a call, or visit the SOMAH website to see case studies, videos, and testimonials from different developers and tenants who have participated in the program. But without further ado, let's make some time to pop into the Q&A. I think we have a few questions. The first one I'm seeing here is probably for Jack, but what are the space requirements for heat pump water heaters, and is there a limitation on how many units one heat pump water heater can support?
Yeah, happy to answer that question. So in terms of limitations, physical space for the storage is really your driver in terms of restrictions for heat pump water heaters. They are, people have made heat pump water heaters that are large, that can serve 200, 300 units with a single heat pump water heater. However, with a heat pump water heating system, you need increased storage. And I don't know, Mark, how many TNDC central heat pump water heating projects do you guys have now? Like 9 or 10? Tenderloin Neighborhood Development Corporation, if you've ever been to the Tenderloin, those buildings are old. Those buildings are compact, and we figured out a way to find places to put those storage tanks in your buildings. And sometimes it takes a creative solution, but yeah, if you want to share a little bit insight on that.
Yeah, I mean, we've installed equipment on the roof, we've installed equipment in air wells, we've installed equipment where we could find space, especially like Jack said, we have buildings anywhere from 124 years old to tomorrow in our portfolio of buildings. So each building offers its unique challenges. I will say on the sizing of the heat pumps, you can also stack heat pumps. So you can have multiple stacks. There's a brand called Sanko heat pumps that we have in some of our buildings, and they're stackable. So you can have a wider array of operational capability with that. The smaller ones also help to fit them in different sizes. The tanks are really the ones that take up a lot of space because the heat pumps are slower to heat the water, so you have to have more storage capacity for that water so that you have that water available.
Thank you both. For the sake of time, last question, but Mark, do you happen to know what the cost range for a building management system is upfront and what monthly charges are? I know it might vary by kind of choice and platform.
Yeah, I mean, there's a lot of variables in the size of the building, it's a lot of times it's built on how many points, and a point is a data point. And so the number of points you get, you're going to increase the cost. So I've spent anywhere from $50,000 on a smaller control system to $200,000 on a larger control system. It really depends on what you're buying, and the number of points you're bringing into the system affects that change. In terms of the contract amount, it also depends on who you're bringing in. So there's proprietary systems that make it very difficult to go out, and there are non-proprietary open systems. So if you look at Tritium, Niagara is a more open system, whereas a Siemens Apogee would be a closed system. There are different types of programming language to think of as well. You're always going to have a service contract with a controls provider. And that can range anywhere from a typical $250, $300 an hour sometimes. It depends on the contract you negotiate. But there is preventive maintenance on the control system as well that needs to be conducted. And that preventive maintenance is typically conducted by a vendor that you hire. And where they do data management, data integrity, they clean the panels, and they make sure everything's running up to snuff. So it's a wide range. But that's why I say start small. You know, if budgeting is just do your heat pumps and get a controller and an interface. And then you can bring that person in and say, I want to do the air conditioning unit now. I want to do this piece of equipment. Now I want to do my pumps, and start integrating that equipment. It doesn't have to happen all at once. You can scale it up. And that's the way I'd recommend it. That's the way we're doing it at TNDC. And I think it's a great approach to doing that. And it keeps you on that path of continuous improvement.
Great. Thanks, Mark. And also a plug for a lot of our clean energy programs here as well. They all include technical assistance. So if there are questions around this, I'd recommend connecting to folks like Jack over at AEA who are working on these programs, who can help troubleshoot and give an idea based on what they see in the field as well. Always giving them a shout out, and the partnership's here to help as well. But I know we're a little over time, so want to be respectful. I know folks are probably eager to head over to lunch, but thank you, Mark and Jack, for sharing such great insight. And thank you all for attending. As a reminder, all of the recordings will be made available on the California Housing Partnership's YouTube page, and all attendees will receive a copy of the slide deck early next week. And I did include a helpful resources page where Jack's presentation last year with that deep dive on technologies is linked, as well as the entire series from 2024, as well as a few of our other electrification and decarbonization reports over here at the partnership. So feel free to use those as resources, or contact any of the folks here today if you have questions or want to chat a little bit more. But thank you all. Thanks for joining. I hope you found this helpful, and I hope you have a great rest of your day and weekends.
Thank you, everybody.
Thanks, everybody.